For this video, we're looking at crossbridge cycling of the muscle. What you're seeing here, this purple, is going to be the thick filament. It's comprised of the myosin subunits. You can see a myosin head is coming up right here. The thin filament up here is comprised of the green subunits, which are going to be actin. You have this orange line, which is tropomyosin. And then you have this small unit here and one more here, which is troponin. Now you can see that the myosin head is currently bound to the actin subunit. One thing to note, each actin subunit has a binding site. You can see this darker green right here. That is the myosin binding site on actin. Now the reason it's exposed, the reason it's available for myosin to bind, is notice we have these calcium ions floating around. When calcium ions bind to troponin, so they increase the concentration and have a larger number binding to troponin, this causes troponin to go through a conformational change. Basically what that means is troponin is going to change shape. As troponin changes shape, it pulls the tropomyosin out of the way. That means the tropomyosin is now moved out of the way, exposing the binding sites on actin. So that means that calcium is pretty important, because without the calcium, we wouldn't be able to move troponin and change its shape, wouldn't be able to pull tropomyosin out of the way, exposing the binding sites. And if those binding sites were not exposed, you could not have the myosin head binding. So now, all that's set, the calcium's in high enough concentration, it's time to start crossbridge cycling. So we have our one single crossbridge here. In reality, you'd have multiple crossbridges coming at all different directions, all different angles. But for simplicity, we're sticking with just one for now. You notice that there is ADP, adenosine diphosphate, and then a free phosphate, that P subscript I. Those two molecules are going to release or leave the crossbridge site. When they leave the crossbridge site, notice how the myosin head has moved. The myosin head is now in the power stroke. What that means is the myosin head has moved from over here in this direction. It's pulled this tropomyosin and this actin and this troponin, the entire thin filament basically, has been pulled along. That means it's moving it or sliding past the actual thick filament. This is where the idea of sliding filament theory comes in. The thin filament is sliding past the thick filament. The myosin head, going into the power stroke, has pulled it past. Once that's completed, the ATP, adenosine triphosphate molecule, will come in and attach to the myosin head. The myosin head will then release from the thin filament. Now again, in reality, you're going to have multiple myosin heads all attaching at different points. That means there will always be some myosin head attached. Because if not, if this ever occurred and you had 0 myosin heads attaching, what would happen? It would simply allow the thin filament to slide back to rest. So you always have to have something attached here to allow it to stay in place. But again, we're focusing only on one at this time. So this one, ATP, causes release. That ATP will be hydrolyzed down to ADP, adenosine diphosphate, and a free phosphate. By going through hydrolysis, think hydrolysis, water breaking, you've broken the bond, you released the energy. By releasing that energy, You're now taking the myosin head, which is in the power stroke position, and moving it back to its cocked position, or its high energy position. It's at this point the myosin head is ready to bind again and go through another power stroke. So what we're really looking at here is we're looking in this diagram at the bound myosin head with ADP and phosphate. We then go through the power stroke, ADP and phosphate are released, ATP comes in, causes the myosin head to release, then goes through hydrolysis to ADP and phosphate, which gives the energy to reset the myosin head to its high energy state. Put it all together, here's roughly what we're looking at in the level of a sarcomere. What you're seeing here on the top of the screen is a muscle cell at rest. This is a sarcomere at rest. You have the thick filament right here in the middle, and you can see the thin filaments around the outside. Notice how the thin filaments have a space between them. But as the muscle starts to go into crossbridge cycling, as the muscle contracts, you're going to notice, look at how the myosin heads are binding, and there's no space in between the thin and thick filaments really. They've closed this gap. So as the myosin and the thick filament cause the thin filament to slide over, it's pulling towards the center of the sarcomere. So we have on the left side here, this Z-disc, this is the outside edge of a sarcomere, is being pulled towards the middle, this M-line or H-band. The right side here, this Z-disc, is being pulled toward the center as well. So overall, the entire sarcomere from Z-disc to Z-disc is going to be shortening. That means the muscle is contracting. This is how crossbridge cycling is occurring.